Hey, welcome back, guys. So we want to go over another two-sample hypothesis testing situation. And that's known as the case where we're testing for difference of means, but our samples are dependent. This is also known as matched pairs or matched paired t-test. So let's get started and take a look at how things work. So what do we mean by dependence? Well, by dependent, we mean something like this. If each member of one sample corresponds to a member of the other sample. Think about something like, how about a weight loss program? So you've got, say, 40 people and their weight is going to be tracked over, let's say, the next, 10 months. So you have their weight currently, and then 10 months from now, you record their weight again. Well, we want to match those up, right? If I didn't match those up, I could have someone who lost weight matched with someone who also lost weight, but because their weights were different to begin with, it looks like they gained weight, right? We want to make sure that the individual person's two weight measurements go together. That would be a meaningful comparison, right? And so that's what we mean by a matched pair. And they're dependent samples because there are two values corresponding to each member in the study, right? So you have these two samples, but the values need to be matched with each individual. Maybe tracking vocabulary size among children, or a type of pain medication, let's say. These are all examples of where you could match pairs with dependent samples. What are the requirements? Well, we're going to conduct a t-test, and your first first thing to notice here is that I'm talking about a t-test, which we've done for single sample. So what's going to happen is we're actually going to wind up looking at taking our two samples and creating a single sample of differences. And so here are the conditions. Samples randomly selected, or simple random samples, I should say, dependent, and then this typical condition, greater than 30 for sample size or normality. What is our test statistic? Well, it's this D bar, literally read D bar, as I went to D bar. I'm kidding. That's how you read it, D bar. And it is each of these here, right? These D's are all differences. So we're adding the differences and dividing by n. It's an average difference or mean difference, hence D bar. And once we have that, here's our test statistic, okay? And again, this mu D, we operate under the assumption that there is no difference, so that will always be 0. Let's take a look. Physical therapist suggests that soft tissue therapy and spinal manipulation, that sounds painful, help reduce the lengths of time patients suffer from headaches. The table shows the number of hours per day 11 patients suffered from headaches before and then 7 weeks after receiving therapy. Test the therapist's claim that alpha equals 0.01. I will also add that you may assume normality. Okay. Well, like all hypothesis tests, let's start with our claim. So what would it mean for the therapy to help? Well, it would mean that the amount of time you suffer after the therapy will be less than what you suffered before. So if you did after minus before, that value would be negative. In other words, the mean difference is less than 0. You could also do an equivalent test and say, or claim and say, well, that means that the time before is larger than the time after, and you would have a right-tailed test. It doesn't matter, but I want to set this up because it's going to educate where I put my critical value. So I've got my null, which is going to be mu D is equal to 0 or greater than or equal to 0 if you want. And my alternative, less than 0. Now, this is left-tailed, my degrees of freedom, well, we have 11 pairs, so 10 degrees of freedom. Let's set up our distribution. So my entire area is going to sit in that tail. And here's my critical T. Of course, my fail to reject region. And again, this should all feel very familiar, okay? So I'm going to come over to my calculator. Might help to share my calculator so you can see it. And let's go to, oops, my distributions, my inverse T. That area to the left is 0.01. I have 10 degrees of freedom. So negative 2 point, if I'm rounding, 764. Negative 2.764. Okay. Well, now I need my test statistic, right? Or my standardized test statistic at that. So what I'm going to do is I am going to place this data into my calculator's lists. This row, I'm going to make L1, and that row, L2. So let's grab our calculator. And I'm going to go to Stat, Edit, and here's my lists. So under L1, I'm going to copy all those values. So 2.8, 2.4, 2.8, and it's important that these are kept in order because they're going to be matched up. 3.2, 2.9, 4.1, 1.6, 2.5. All right, my other column, 1.6, 1.3, 1.6, 1.4, 1.5, 1.6, 1.7, 1.6, 1.8, 1.2, and 1.4. All right, wasn't that exciting? Most exciting moment of the video, watching some guy on camera put numbers into a calculator. All right, so now that the sarcasm is done, let's take a look at what we got. We have these two lists of values. Excuse me. Now, what's meaningful is their differences, right? That's what I want to look at, the differences. So in L3, I'm going to compute those differences. Now watch what I do. In L3, I've highlighted L3, right? So I want L3 to be L2 minus L1 because we decided ahead of time to do after minus before. Remember, our claim is that the mean difference is less than 0. So after values should be less than the before values, making those differences negative, okay? Like I already said, we could have done it the other way as well. This is just the way we decided to set it up, or I decided to set it up here. So I have to keep that in the back of my mind. I'm doing after minus before. And so where are my after values? Well, they are in L2. So second, and then the 2 key will access L2. And then minus second L1. There are all my differences, okay? Now, that D bar, I could actually get from 1var stats, right? I could do 1var stats on L3, right? Because I want the differences. And that negative 1.25, that's my X bar, my mean, which in the notation of the two sample t-test for dependent samples, we call it D bar, okay? But even that's more than I really need to do, because essentially I'm just performing a t-test on the differences. So let's go to t-test, stat tests, number 2, t-test. And I'm giving it data, right? Not stats, I'm giving it data. I've got the raw data in my calculator. My mu0 is 0. My list, right? Where did I put the data? Now be careful. I have data in L1 and L2, but the data that I want is in L3, the differences. So second, 3. Always leave this frequency at 1. My claim, my alternative is that mu is less than 0. And we calculate. Negative 9.429. Negative 9.429. And again, that came from a t-test. Okay. Well, where is that negative 9.429? Well, it's way out in the rejection region. So we reject the null. And we can say at alpha equals 0.01, there is sufficient evidence to support the claim that the treatment reduces length of headache. Okay. All right. Let's try another one. Back to Guinness. Wonderful beer. William Seeley Gossett, remember the guy who worked for Guinness, came up with the student's tea distribution. He tested to see if a plot would yield more corn if the seeds were kiln dried first. The results are in the following table. So we had kiln dried seeds versus the regular drying, and from these they recorded the yield, how much they got from how many pounds per acre. And so these are their 11 plots. Again, we're going to assume normality. And we're going to test the claim that the kiln drying results in greater yield, meaning that if we take kiln minus regular, that should be positive, right? You should get more. And so there's my claim that the mean difference is greater than 0. So let's do our hypotheses. My claim, of course, is my null. And so my alternative, I'm sorry, said that backwards. My claim is my alternative, and my null then will be this. I have, again, 0.01. I have 10 degrees of freedom. Oh my gosh, I am all over the place. This is greater than 0. What I'm saying and what I'm writing, not agreeing. Apologize for that. Okay, and so now we're going to set up our distribution. Hopefully yours is prettier than mine. Okay, so there's my area, 0.01. Here is my fail to reject HO. And here's my critical T. So I'm going to go over to my calculator to get that critical T. So second distribution, inverse T. The area to the left of my critical is 0.99. I have 10 degrees of freedom. So we get 2 point, well, no surprise, it's just using symmetry. Since our sample sizes were the same, it's like the last one, right? But positive. 2.764. 2.764. Okay. Now we're going to run a t-test on the differences. Okay, so let's come back to the calculator. And let's go put our data in our calculator. So first thing I'm going to do, come over here to stat, edit, and I'm going to clear these. So clear, highlight the top of the column and hit clear, highlight the top of the column and hit clear. Okay, so I'm going to make L1 my kiln dried and regular L2. So 2009, 1915. Is this as exciting as the last data entry? I don't know. Well, we're talking about corn yields in order to make beer. So I think that makes it by default more exciting. 1925, 21, 22, 1482, 1542, 1443, and 1535. Okay, now let's go to L2. 1903, 1935, 1910, 2496, 2108, 1961, 2060, 1444, 1612, 1316, 1511. Oh man, makes me thirsty. I need a Guinness. All right, L3. Now I'm looking at differences, right? And the way I've decided this is I've established, before I even started my test, right? I established kiln minus regular. So my kilns are in L1. So I'm going to have L1 minus L2. And there's my differences. Okay. So now we quit out of here. And we go to our t-test. And again, we have data. That's 0. My differences are in L3. It's right-tailed this time. And we calculate. So T is 1.690. 1.690. Apologize for my writing here. Let's try this again. Which is very much in the fail to reject region. So at alpha equals 0.01, there is insufficient evidence to support the claim that kiln-dried seeds have a higher yield than regular. Okay. All right, guys. So that's hypothesis testing, matched pairs t-test. Okay. Go back and work through those, and keep working as many problems as you can, and we'll just keep plugging along. I will see you guys very soon. Bye-bye.